Okay, so in this section we're looking at horizontal and vertical lines. So if we consider the equation y equals 4, at first it may not be clear exactly how we should complete a table of values because there's no x in the equation. However, if the equation means that no matter what the value of x is, y is always equal to 4, if I plot my table it would just look like this. So if I go from x equals minus 3 all the way up to x equals 3, the y doesn't care what x is, it's always just 4. So if I plotted this, all of these points, I end up with just a straight line. But in this case, it's a straight line that's horizontal, and it never actually touches the x-axis over here. So y equals 4 would just be a horizontal line. On the flip side, any horizontal line will have the equation y equals k. A vertical line will have the equation x equals k. K here is just a number. We use k as a constant, so it's not a variable, it's not like an x or a y. K is just any number you can think of. So, for example, in the top one, the horizontal line, our k would be 2, so that equation of that horizontal line would be y equals 2. The vertical line here, you can see that it passes through 3 on the x-axis, so here k would be 3, the equation would just be x equals 3, and that's my vertical line. So here I want you to draw the graphs of these lines here. So they're either going to be vertical or horizontal, and that's something you need to think about in terms of this one gives you a y value. So if it gives you a y equals, you know that on the y-axis it hits at y equals 1. So if it touches there and it never crosses x, it has to look like that, right? A horizontal line, and so on. So that's what I want you to do first, and then keep going on with the video once you've got past that point. Now in question 2, on the same set of axes, draw the graph of x equals 4 and y equals minus 3. Write down the coordinates of the point where the lines meet. So one's going to be vertical and one's going to be horizontal, which means at some point they're going to cross over, and I want you to write the coordinate where they cross over. That's the point where they meet. So once you've done this, it may not seem particularly significant to you right now, but it's actually very useful finding this intersection point, and we're going to talk about that a bit later on. So what you've actually done is you've solved two equations graphically. It means that you've found the point where the two lines intersect, which is just another way of saying where they cross paths. An intersection point is given as an x, y, just like any other point, so it's a coordinate. An intersection point is a coordinate of intersection. For example, if we had the line y equals 3, it's a horizontal line that passes the y-axis at 3. And we also had x equals 3, which crosses the x-axis at x equals 3. The intersection point would be where they cross, which you can see from the graph is just 3, 3. That's our intersection point. So, now if we want to know whether a point is on a line or not, there's two methods to this. We can either graph the line and then plot the individual point and see if it is touching the line, or we can do it algebraically. Let's look at the equation first. If, for example, I have y equals 2x plus 1, this tells you a few things. Not only does it tell you what the line looks like, but without even drawing it, it tells us every single point on that line. It tells us what the value for y is at any given x and vice versa. So right here, if I just make up an x, say 1, I know that that's talking about on the x-axis. If I plug in a 1 here, it's 2 times 1, which is 2, plus 1 gives me 3. So y equals 3 when x equals 1. That's 1 point on the line. And I could do this for any x I can think of, or I could flip it and I could do it for a y value. Substitute a y in and rearrange to get x, just like we've done in the earlier algebra, and I'll have another point. For example, if I had this equation, y equals 2x plus 1, if I want to make a table first, that's fine. I go from minus 2 to 2, for example. As I calculate my values, I just substitute the x into the equation and figure out what the y is. So this equation will tell us all the possible values for y if we give it a value for x. It's like a rule, basically. It says for any given x, the y is provided by the formula above. So if we plug in minus 2 for our x, we would have minus 2 times 2 plus 1 gives us minus 3. And I can keep going through my table, and I'll have all of these points. So now if I plot it, this is what my line looks like. All I've done is I've plot my table of points from the equation, and I get a straight line, as I would expect. So here's an example in a bit of a scenario. If you were running in a 3-kilometer race, and you need to complete it by 8 minutes in order to break the world record, you can plan out the route and break it into little intervals to keep your pace and help track your progress. So if you were timing as you were running, and you knew what distance you were at, it's your way of saying, am I ahead of time, am I behind time, or am I just on time to break the record? So the following table is your checkpoints. This says, at 1 minute, I should have travelled 500 meters. After 2 minutes, I should have travelled 1 kilometer, and so on and so forth. So ultimately, by the 6th minute, I should be at the 3-kilometer mark, and that means I'll break the record. So now, if we plot these points, I've got x, which is the thing that I'm changing, right? The time that's passed. My x would be 1, the distance would be 0.5. So here I've got 1 and 0.5. So just like we've plotted points before, I plot it on the graph, and that's my point. And I do this for all of my points here, and I end up with this line. So now, this is where I started, right? When time was 0, that's before I've started the race. I finished the race at 6 minutes, which is where I've run 3 kilometers, which was the objective. So that's my finish, that's my start. This is the line that joins all of my checkpoints. So this is the line of my world record effort. If I'm on that line, I'm going to break the record. If I'm off the line, I'm either faster than the record or I'm slower and I'm not going to break it. So, let's look at an example, and I'll move this down here. If the time was 4 minutes, 4 minutes into the race, I have run 1 kilometer, and I want to know, am I on track to break the record? I look at the coordinate down here at 4, and I've run 1 kilometer, so I look at 1 here, I'm actually right here. So that's the distance I've travelled, that's where I am, and I should be up there. So I'm at the 0.41, and I should be at the 0.42. So I've only travelled 1 kilometre in that time, and I should have travelled 2 kilometres. So I'm actually behind time. At any point, or any point that's not on this line, means I'm either ahead of the time or behind the time, like I mentioned before. So in this case, I'm too slow. Both examples here, I'm either ahead or behind. On time is on the line, ahead of time is not on the line, and behind time is not on the line. In this example, obviously being ahead of time is okay, but the main thing we're looking at for this example is whether or not I'm on the line. If after 5 minutes I've run 2 kilometres, am I on time? Well, there's 5 minutes and 2 kilometres, right? So if I move myself out of the way, there's my 5, there's my 2, I move across, and that's my point. So now the question for you is, am I ahead of time or behind time? I'm definitely behind time, right? Because I've run a shorter distance than I should have. What about if after 3 minutes I've run 1.5 kilometres? Am I on time? Well, let's look at the point. It's right there, 1.5. So in this case, I'm actually on the line, which tells me that I'm on time. So I'm doing alright here. So if I told you that the equation of this line was y equals a half x, that's just what the equation of this line is. If I was to ask if after 3 minutes I've run 1.5 kilometres, am I on track, which we've done so far, this is actually exactly the same as saying, is the point 3 1.5 on the line? Right? Because I would look down here and I've got 3. I would look at 1.5 and I say, oh, is this on the line? Yes, it is, so I'm on time. That's exactly the same as this, just saying, is this point on the line of this equation? So we can look at it by graphing, or we can simply look at whether a point fits an equation. So a quicker way to find out whether you're on track to break the record or not would be to enter the value, which is your time, into the equation and see if the result is the same as where you actually are. So for example, if this was the equation of the line that you were given, and I said after 4 minutes you've run 1.5 kilometers. Your coordinate would be 4, 1.5. So I can plug in the time, 4, into this equation. And it's x, right? X is time in this case, the thing that's changing. So I would have y equals a half of 4, which we know is 2. So the equation tells me that at 4 minutes I should be at 2 kilometers. But I'm actually only at 1.5. So in this case I'm behind time, or in other words, I'm not on the line because it doesn't agree with my point. Another way to do this is to substitute both values in and see if the answer makes sense. And this is probably the most common method. So, same problem. At 4 minutes I've run 1.5 kilometers. Another way to say this is the point 4, 1.5 on the line of this equation? Plug in the coordinate, as 4 is my x value here, and 1.5, obviously you can see x, y. 1.5 is my y value. So if I plug this in, I get 1.5 equals a half of 4, and that's just going to be 1.5 equals 2. But this doesn't make sense, because 1.5 is not equal to 2. So if at any point I get an equation that doesn't make sense, it means the point is not on the line. However, if I have this point, I do the same thing. I plug it in. 2 is my y value over here. 4 is my x value. I plug this in. I get 2 is equal to half of 4, which is 2. So 2 equals 2. This does make sense, right? Because 2 is definitely equal to 2. That tells me that the point is on the line. So if I substitute x and y into the equation, and the left-hand side equals the right-hand side, then it is on the line. If the left-hand side doesn't equal the right-hand side, it's not on the line. So that's the algebraic method. Here's a couple of practice questions. So is the point 2, 1 on the line with the equation y equals 2x plus 1? So remember the process. I substitute, this is my x into my x, and y into the y, and I just want to know if left-hand side equals the right-hand side. So pause the video before I give the answers for these, and see if you get the same thing. So if we sub 2, 1 into the equation, it looks like this. 1 equals 2 times 2 plus 1, 1 equals 5. This does not make sense, so it's not on the line. For the next one, if I substitute the points in, I get 3 is equal to 2 times 4 minus 1, 3 equals to 7. That doesn't make sense, so that tells us it's not on the line. What about the next point? This looks like a bit of a more complicated equation. I've got a 2x plus a 3y, but I still do exactly the same process. I substitute my x for 1 and my y for 2, and I get this. I get 2 times 1 plus 3 times 2 equals 8. If I simplify that, that actually gives me 8 equals 8. So this makes sense. So it's on the line in this example. Alright, so I want you to have a go at these questions. So they're just determining whether the following points are on the line. So here I want you to do it algebraically. So we're substituting these numbers in to see if it makes sense. And remember, if it makes sense, it's on the line. If it doesn't make sense, it's off the line. So pause here, do these questions, and then keep going with the video. So just as we saw earlier, an equation for a line, which we know as a linear equation, has 1 as the highest power for any variable. So any x or y in an equation does not have a square or a cubed attached to it. It'll always just be by itself. So using what we've done so far, if you were given a linear equation, for example, say y equals 2x plus 1, you should be able to just make up numbers for x and figure out what the y equals for that value. Doing this a few times for different x values will give you points to plot and create the line in which the equation represents in the first place. So now we want to look at using graphs to solve equations. Previously in linear equations we talked about solving an equation algebraically by solving for the unknown. For example, if I had 2x plus 1 equals 3, we can rearrange this using what we know about the inverse operations and algebra rules to get this into x equals 1, which is the solution to the equation above. We could also solve the linear equations graphically by plotting the points and the line and looking for where they intersect, which we now know is just the point where they cross or meet. if I plotted the graphs of two equations, y equals 2x plus 1 and y equals 7 minus x, the graphs would look like this. From the graph, that you can see that the point of intersection is 2, 5. As the first equation is y equals something, and the second equation is also y equals something, this means that the first equation equals the second equation because they're both y. So I could write this as 2x plus 1 equals 7 minus x, because this is y and this is y. The intersection of these two points is 2, 5, so this is actually the solution to this equation here. So, looking at this question, on the same set of axes, which I've given you here, draw the graphs of y equals x plus 2 and y equals 4 minus x. Find the point where they intersect, and then solve the equation x plus 2 equals 4 minus x. So here, you should notice that this is the same as this, and this is the same as this. So it's going to be a y equals y situation, and the answer to this should be exactly the same as what you find your intersection. So have a go at that, pause the video, and find the answers to those questions. In this example, we're doing the same thing. I've got the equation 2x minus 7 equals 5 minus x, and they want you to solve the equation graphically, which means to graph both halves, and also using algebra, so you can rearrange this to find out what x is. So that is the next question for you to do. Pause here and have a go at it. Now we want to use graphical methods, so graphing only this time, to solve the following. So I've got these 4 examples, so you're going to graph each piece, think about what the values would be, and find their intersection points. And remember, the intersection is the solution to the equations.